All right, before we get started, quick announcement on midterm 2. So I posted similar kind of announcement on Canvas, like what we did for midterm 1. The format will be pretty much similar. You will take the exam here in this room. Your TA will be with you to hand out exams and collect them at 12:50 precisely. The exam itself is open book, open note. You can bring anything on paper that you like. But my suggestion is you don't write too much of things on your lecture notes so you know where to find them. So that you're like, basically for a open note exam, the biggest mistake you want to avoid is learning during the exam. It doesn't work this way. You're expected to already know at least which lecture note to go to. The whole point of being lecture, like open book, open note, is for you to refer to like some rigid memory things, like what is the nomenclature of a aldehyde, right? So these are the things, like for example, heptanol, like these are the things we covered before, but in the midterm exam, if you don't quickly remember what a NONE mean, you can go back to the functional group nomenclature and quickly find that result. Right, so the whole point is you don't have to rigid memorize everything. We'll go over all these examples later today. The structure of the exam will be exactly the same, but this time I removed some of the true and false problems because for reactions it's a little bit harder to ask true and false problems. So you will expect 10 multiple choice problems, 4 short answer problems, and then 1 comprehensive problem. The structure is again the same. I was hoping you'd be able to finish each multiple choice within 1 minute, and then 5 minutes for each short answer problems, 15 minutes for the comprehensive, 5 minutes to double check everything. All right, so plan your time wisely so that you know what to expect. What else? I'll be having a buffer lecture this Wednesday going over materials that will be covered on your midterm exam. Your midterm 2 covers material from chapter 4 all the way to chapter 7. So that's acid and base chemistry and everything we will discuss today, right? So acid-base chemistry, physical property, nomenclature of alkenes, reactions of alkenes, reactions of alkynes, and also at the end of today we'll be talking about the alkyne and retrosynthesis. In between these chapters, there's also something called premier, which is arrow pushing and typical reaction mechanism. So that's also going to be part of the coverage of your midterm 2 exam. What else? I'll be host office hour tomorrow, so stop by if you have any questions you want to ask me. Well, other than that, I'll take any questions if you have for administrative questions. Okay, sounds good. So let's get into our today's lecture. So in our last lecture, we went over the class of reaction of alkynes, which is a hydrogenation. So as its name says, hydrogenation, we're adding hydrogens across the alkyne. The special thing about hydrogenation of alkynes is we can form alkenes or we can fully reduce it into alkane. And if we are forming alkenes, then there is stereochemistry we have to take into consideration. Namely, the 2 hydrogens can add onto the same side of your alkyne to form a cis-alkene, or the hydrogens can add to different sides to form a trans-alkene. So in our last lecture, we went over discussion of like catalytic hydrogenation. So using palladium as a catalyst or nickel as a catalyst, we can fully reduce the alkyne all the way into all saturated alkenes. Alternatively, the usage of your Lindlar's catalyst will be able to reduce your alkyne into cis-alkene. All right, so this is the cis coming from. We also mentioned the potential of hydroboration protonosis reaction that also forms cis-alkene. So we now have 2 ways to form cis-alkene using Lindlar's catalyst or hydroboration protonosis. And we have 1 way to form a fully reduced alkane. So in today, before we went into retrosynthesis, we want to quickly go over a reaction that forms trans-alkene. And we will discuss the mechanism of the formation of the trans-alkene and see what's the origin of that stereoselectivity. So that reaction here is called dissolving metal reduction. Or if we read it, we're seeing reduction of an alkyne with sodium or lithium. So your alkali metal in liquid ammonia will convert an alkyne to an alkene with anti-stereoselectivity. All right, so we are forming the trans-alkene, or the two hydrogens add on to different sides of your alkyne. And let me finish before I take any questions on this part. Now, when we're reading this kind of reactions, we have these are my reactants, these are my products. And in this case, you want to keep in mind that whenever you're writing this kind of acid-base you're writing these kind of chemical reactions, your reactant and product need to be balanced. You do not have to write the solvent into your reactant, but keep in mind you want to write balanced chemical reactions. All right, question? I think it's the light. Let me see. Works better? Okay, sounds good. All right, so for this reaction, in organic chemistry reactions, sometimes we'll give you the reactant, we'll give you the reaction condition, we ask you to predict the product. So that's one way we can ask a question. Second way we can ask a question, we give you the desired product and we give you the reactant. We ask you to predict what is the reaction condition to achieve this kind of transformation. Or we give you the product and we tell you what are the possible reaction conditions. We ask you what are the potential reactant we need to use. That's the third way of asking. And in addition to all that, we might also ask you what is the reaction mechanism, and that's the mechanism we will be discussing. That's the arrow pushing. So if we didn't say write out the full reaction mechanism, you do not have to show the mechanism for every reaction. All right, so that's just a quick introduction here. All right, but what is, yes?
What are mechanisms we haven't been introduced to, like for like the last one, with like the limiters, catalysts and stuff? Do we need to know those mechanisms?
No. If the mechanisms are not in our lecture note, you don't have to know that. All right. So for this one, you do have to know, because this one we want to use the mechanism of the dissolving metal reduction to illustrate what is the origin of the trans-hydrogenation reactivity or selectivity in this case. Now, thinking about the reaction mechanism here, this is a little bit special reaction mechanism because we're dealing with one electron processes, or at least we're dealing with one of the, this is the first introduction of one electron processes. So we used to write the arrow pushing of like doing the double-sided arrow. So now the reactant itself, we're reacting a sodium metal with the alkyne. So looking at the sodium metal, that is one of our alkali metal. So namely, my sodium metal only have one valence electron. So in this case, the first step is a one electron process. So we use these kind of single-sided arrow to show the movement of the electrons. Right, so this is what we are saying, is my sodium is giving its electron onto this carbon here. Let me do it more accurately. So my sodium metal is donating its electron into that carbon on the alkyne, and we're forming a alkylocarbanion. So this process is called a one electron reduction. And predicting what is going to be formed based on these arrow pushing. right? So again, what we're thinking is the electron in this triple bond in one of the, okay, so for the two electrons in one of the pi bond of my alkyne, one of it go to the left carbon, and that's gonna form a radical. The other one go to the right carbon, and the electron in the nitrogen also go to my right carbon. So what are we gonna form? So we're gonna have R, and here we have a single electron, which is a radical. The double bond remains where they are, and on the right, we have a carbon-centered anion and my R prime. Also, I have my Na plus around. All right, so in this case, there's a resonance structure we can potentially draw, which is, well, what if we are pushing the electron here? To have the anion on the different carbon and the radical on the right carbon. And these carbanions are very strong base. Right, so the basicity sort of works similarly to the acidity trend that we discussed. More stable the conjugate base, you're looking at stronger acid. In this case, more stable the conjugate acid, like the CH group, if we're forming a new CH bond, then we're having a stronger base. But for now, just knowing that these carbanions are very strong base, that is even more basic than ammonia, which is a molecule that we typically consider basic. So the next step will be an acid-base reaction. Right, so here we have the carbanion moving the electrons to form your R carbon double bonded, NH2, carbon, R prime. Now, whether the acid base takes place via this resonance or this resonance, depending on the substitution on that carbon. So that's the regional selectivity that we did not discuss. Yes? No, we don't talk about Markovnikov selectivity in this case, because after all, both of them will have hydrogen added to them. So regional selectivity doesn't really matter. Yes.
I was just wondering if the electrons are donating to H, why is it R, CH, and NH2 as a ion in the solution? Like, why would the C bind to the H because you're giving it electrons and the bond is broken between that and NH2?
That's a good point. I actually should write it as a hydrogen. Thank you for that. I think I made a typo in my annotated note as well. So in this case, when we're looking at this specific reaction, one of the potential questions we could ask you is, what is the nature of this reaction? Now this reaction, we're talking about transfer of a hydrogen. So this is a Bronsted acid-base reaction. And in here, which group is my Bronsted acid? So which one is my Bronsted acid in this acid-base reaction? NH3, right? So this one is my Bronsted acid. And this one is my Bronsted base. And then looking at this intermediate, which is an alkynyl radical. And this is the origin of our stereo selectivity, because after formation of this new CH bond, we end up having a radical group or an alkynyl radical. And the trans alkynyl radical is favored. And because the trans-alkynyl radical, or this hydrogen, will like to be on the same side of whatever substitution on the other carbon, the radical will be on the same side with the R group. So what's going to happen next? Well, we will have another 1 electron reduction. With sodium. And we do the same kind of arrow pushing. The electron goes onto this carbon to form a carbon-centered anion. And next step becomes pretty straightforward. Another Bronsted acid-base reaction takes place with ammonia. And we have Na plus around. And we end up generating our product, which is the reduced which in this reaction, we're reducing an alkyne with an alkali metal, sodium or lithium, in liquid ammonia to form your alkene product in a trans stereoselectivity. Yes?
Going back to the resonance structures, so you were saying, how do you tell which one you would use?
It doesn't matter. Like if you think about doing the addition from this carbon first, you'll be generating a different product, right? But effectively, these two will still be trans to each other. So what I'm saying is, let's say, let me use a different color. Let's say from here, I have a NH3 attacking here. What are we gonna form? We're gonna form R carbon radical. And then here we have carbon, R prime, and then hydrogen. Okay, I want to put it this way. All right, but in the second step, we'll be replacing this one with a hydrogen as well. So regional selectivity doesn't matter in this case, because after all, we're adding 2 hydrogens onto both carbon. There's no regional selectivity in this reaction.
So we wouldn't care about like the stability of the radical, like the one that we learned?
It's like we're getting the same product, nevertheless, so it doesn't matter. Yes?
So is the reason the hydrogen is on the same side as the R group because it reduces the amount of strain?
The best way to say, so this one we're just saying the alkynyl radical will favor the conformation so that the radical will be trans to this hydrogen. Like we want this radical to be next to, neighboring to a R group, not neighboring to a hydrogen.
Can you draw that completely like whole product? Just so I can check it.
This one?
Would it be attached? Oh wait, never mind.
Okay.
Is having the plus 2Na plus 2H3 similar to having it on top of or below the arrow?
So in this case, I like to write reactant as like here. Your NH3 will be solvent and reactant in the process. So there are different ways to draw it. I like to write fully balanced chemical reactions. But if you write it in this way, in which you're writing the reagent, which is acting both as a solvent and a reagent on top and below the arrow, that's also okay. But for sodium, which is a like straight reactant, you want to make sure you add it to the left-hand side of the arrow. So the whole point of writing it this way is if you think about you're doing the experiment in the lab, these are the things you'll be putting into the test tube with the solvent around. All right. Okay, one more question.
So is the reason that we want our electrons next to the R group, is that because of like hyperconjugation with the ion, or is it something else?
It's related to hyperconjugation, but I'm not going into too much detail into the actual stability of the alkynyl radical. It's a little bit above the 30A level. All right, so let's get started of putting everything together, right? So far, we went over a lot of different reactions. So in alkene reaction, you have all the addition reaction, ozonolysis, oxymercuration. Alkyne, you have alkylation, nucleophilic substitution, all of these reactions. What is the ultimate goal? So the ultimate goal here is we as organic chemists, we like to make molecules. Like we actually want to synthesize molecules. Or this is gonna be our first introduction into organic synthesis. Say, how do we build a molecule from some given starting materials? I put two examples there that we will be going over together. But before we go over those two specific examples, let's think about what exactly is needed to do that kind of analysis, or like what is the criteria we're looking after. So what we're saying here is that a successful synthesis should have several different criteria. That is, we want to get as much as yield as possible. So if one reaction is only a 50% yield and 50% byproduct, that's not ideal. And also, we want to have as much control as possible over both stereochemistry and regiochemistry when necessary. And lastly, we want to do minimal damage to the environment. Namely, we want to have less steps, as little as possible. And well, green synthesis is a little bit beyond the 30A level. None of our reactions are, well, some of them are used, but most of them are not actually used in modern organic chemistry lab nowadays. But we as organic chemists, we still want to make sure we're using green synthesis as much as we can. And the strategy we'll be using is called retrosynthesis, which is going backwards from a target molecule to all the starting materials that we want. So for retrosynthesis, typically we write it the reverse. Like this is the one we want. Like we say, this is my target molecule, which this one is, well, styrene. It's like a complicated natural product that we want to synthesize. We use this type of arrow. So these are specific arrow for retrosynthesis. On the left-hand side, towards the target molecule is open-ended. On the right-hand side, that's like an arrow there. So it's a very specific shape of arrow that we use. Note that we already went over different types of arrow we discussed in organic chemistry, right? You have electron pushing, you have resonance, which is double-sided. You also, for electron pushing, you have double-sided and one-sided for 2 electron and 1 electron process. And this is the specific arrow we use for retrosynthesis. So on the left-hand side, that's our target molecule. And here, this is our intermediate. Or it's still a product of a reaction, right? But it's just like an intermediate product. And at the end, we have like building blocks to get to this intermediate. All right, I'm not going to ask you to do retrosynthesis for this molecule, but let's look at some simple examples into what is behind the mind of chemists when we're actually designing roads for retrosynthesis. So there are 2 major criteria we want to take into consideration. One is called the carbon skeleton. So namely, how do we put the molecules together? Right now, the only reaction, well, we have 2 reactions that alternate the carbon skeleton. We have alkylation of the alkynyl anions to form new carbon-carbon bonds. We also have ozonolysis that cleaves the carbon-carbon double bond to form carbon-oxygen double bonds, right? So we have 2 ways to manipulate the carbon skeleton. We'll go over the list of reactions before we look into the examples. And secondly, after we finish alternation of the carbon skeleton, we'll start to work with functionals. Like what is the function, what are the functional group in my reactant? What are the functional group in my product? How do I convert an alkene into alcohol? How do I convert my alkene into aldehyde in a controlled fashion? So 2 different steps. 1, analysis of carbon skeleton, and 2, how to convert different functional groups from one another. So let's look at a quick review of all the reactions we discussed so far. So this is going to be a quick flashback. These are everything like on this slide you should already know. If you don't know, well, you have to review it. So for carbon skeleton, we're talking about alkylation of alkynyl anions, right? So we're talking about the alkyne, especially acylidene, or alkynes with terminal alkynes with terminal CH bond. Upon deprotonation of that acidic terminal CH alkynyl hydrogen, we're getting a very strong nucleophile that reacts with a haloalkene via a nucleophilic substitution reaction to form the elongated carbon skeleton. And your alkylation can be repeated as long as if your terminal alkynes are available. So you want to manipulate the reaction carefully to make sure you have limiting reagent around. And also for carbon skeleton, we also have alkene reaction, which in this case we have our ozonosis. And I think the ozonosis is great, it's not on here. But for ozonosis, you know what we have, right? So we have like a carbon double bond and treat it with O3 and H2 and O2 workout. And you end up forming the 2 the 2 carbonyl group or the carbon oxygen double bond. So alkylation of alkynyl anions makes longer carbon skeleton. Ozonosis makes shorter carbon skeleton. So these are the 2 toolbox we have. Next step, how do we manipulate with functional group? Well, so functional groups, these are the alkyne reaction we went over in our today's chapter 7 lectures, right? So you can have reduction. So depending on the condition you're using, we just went over the dissolving metal reduction. In that reaction condition, you have sodium, you have NH3, we're forming the reduction in a trans stereospecific fashion. With Lindlar's catalyst, you're reducing your alkyne with a cis selectivity. And you can always reduce it to further to alkane if we want alkane as our product. And then for HBr addition, if we have excess of HBr or H2 as your reagent, you're forming the dihalogenated alkane product. And then we have addition reaction, so treating your alkyne with your mercury sulfide under acidic condition, we're transferring your alkyne into a ketone after the formation of the eno and the eno-keto tautomerization. Alternatively, the addition of water onto alkyne can take place at under base condition with the hydration reaction. So under basic condition, the keto-eno the hydroboration followed by keto-eno tautomerization gives you aldehyde as a product. And keep in mind the selectivity between these 2 reactions, right? So the acid catalyzed oxymercuration, that's Markovnikov selectivity. So your OH is on the internal carbon. For hydroboration, it's anti-Markovnikov selectivity. So your OH is on terminal carbon and thus being transferred into a aldehyde. And the name of the functional group, that's something you should be already familiar with, right? So this one is aldehyde, and this one is ketone, alkene, haloalkene. All right. Similarly, for alkene reactions, we already went over this table in our previous lecture. Highly recommend you go back and double check this table to see like what's going on in there. So now let's look at our two examples together on the board together. Again, I'm gonna keep this one with you, which are, what are the steps to approach this kind of retrosynthesis problem, right? So the step one, you want to draw the structure of your product and starting material available. So that's why we spend time on nomenclature. Two, analysis on different possibilities and see how do you write out, how do you adjust the carbon skeleton and functional group. And three, write out the full reaction. So let's just do that together. So example one, it asks you to prepare two heptanol from haloalkane and acetylene. So what are they? So we want to get two heptanol. So hep, we have 7 carbon, 1, 2, 3, 4, 5, 6, 7, and oxygen. And we're trying to form the two heptanol. That's my retrosynthesis arrow. Actually, it's a little bit different. I'm not very artistic on that. From haloalkanes, so some kind of R group attached to a X, so haloalkane, and acetylene. So that's what we have. And well, yes,
I'm just curious, does the arrow not go the other way?
no. So retrosynthesis, keep in mind, we're doing the arrow this way, because this is what we want. All right, the other side is like double-sided.
In the slide, that's the other way.
Wait, let me double check on that. Yeah. Thank you. Okay. All right, getting started on this. So then we're doing the analysis of thinking about what are my carbon skeleton, right? We comment on here, we have 7 carbon, 1, 2, 3, 4, 5, 6, 7. And on the right hand side, I don't know, I just know my acetylene have 2 carbons, and in here, well, you derive it backwards. So I know my R group will have 5 carbon in it in a linear fashion. So this one will be my 1, 2, 3, 4, 1, 2, 3, 4, 5 to a BR group. Right, so I want to use my 1 bromopenting as my reagent. So that's the analysis of my carbon skeleton. And let's just finish this one. Now, next one is how do we work on the functional groups? So what do we have? Now we start from this one, 1, 2, 3, 4, 5, 6, 7. So that's where I start. And I know I want to first construct my carbon skeleton. Wait, so sorry for that. So we want to convert my carbon skeleton that we already derived into that ketone. So how do we work from an alkyne into a ketone? So the logic is behind it this way. We know that we want to elongate my chain, right? So the first step must be a alkylation. So that means we'll end up with an alkyne as my intermediate. So the question becomes, how do we translate an alkyne into my functional group, which is ketone? So this one is 1, 2, 3, 4, 5, 6, 7. And this must comes from alkylation. So how do we translate my alkyne into a ketone? So that goes back to our list of reactions that we have. So coming back, we'll be like, okay, we have an alkyne. You want to convert it into a ketone. So that's the addition of water under acidic reaction. Yes? Okay, so this one is this way. We know we start from acetylene, reacting it with a haloalkane. What is the product coming from my acetylene to my haloalkane? So for this reaction, this is an alkylation reaction. So I know that I want to have like a base condition, like NaOH, and I have my process coming from like Rx, and then my acetylene is being deprotonated, and we're coming this way. So specifically in this reaction, the intermediate will be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, hydrogen. So that's how we get this terminal alkyne must be my intermediate. All right, and then the question becomes, what is going to convert this terminal alkyne into the ketone that we want? Now we look at the selectivity. We're forming this ketone, so we're looking at the OH adding to the internal carbon 2. So this must be a Markov-Nikov selectivity. So for this reaction, we're looking at the acid catalyzed hydration of your alkyne. All right. Or for this total synthesis problem, we'll end up writing what we get, which is now we have solved the puzzle by writing all the arrow. We can write the reaction condition that we want to use. So the first step is deprotonation with NaNH2, which is a super strong base. You get the alkynyl anion, reacting it with the haloalkane. And this needs to be one equivalent to avoid overreaction to get 1, 2, 3, 4, 5, 6, 7. So that's my internal alkyne intermediate. And then under condition of your HgSO4, H2SO4 in water, it undergoes hydration of your alkyne to form your ketone product. All right. So the two steps we take, first, skeleton, second, thinking about what are the functional group. Yeah, question.
How did you get the chain with the bromine and from, like you said, you look at the haloalkane instead of
Well, so when we're doing the analysis, remember the first step is analyzing how does my carbon skeleton change. All right, we only have two tools that we can use in our toolbox right now. The tools we have is one, alkylation, which is here, alkylation of alkynyl anions. So this is the elongation of your carbon skeleton. Or we have ozonosis, which is shortening of my carbon skeleton. So you start by counting the number of carbon we have in the molecule we want to build. In this case, it's 7 molecules we want to build, 7 carbon atom we have in my final product. And we look at my starting material. The question gives us our starting material is a haloalkane and a acetylene. Now for acetylene, we know it only has 2 carbon, so my haloalkane must have 5 carbon. All right, so that's how we get the 1-bromopentane as our starting material. And then from here, we into ketone. So that's manipulating the functional group. All right. And let's do one more example together. So this one, second example, this is how do we convert propanol, or how do we form propanol from 3-hexane? So again, we first, very loud, 1 second. Can you actually hear me without microphone?
Yes.
Okay, sounds good. I'll just speak really loud. So first of all, we're just writing out what are the structures from their IUPAC name. So this one you should already be very familiar with. They will be like simple molecules like these, but as long as you know how to draw them, like my 3-hexane, so that's 6 carbon, with my triple bonds at position 3, 4, and well, 5, 2, 6, 1. So when drawing these molecules, keep in mind that alkyne is a linear molecule. So your carbon 2, 3, 4, 5 must be on the same linear, right? So it is incorrect to draw this bond into like something like that's bent. It must be a linear molecule. Now, what is my propanol? So it's propanol. So pro states we have 3 carbon. PANAL, does that say we have a aldehyde? So this one is my propanol. Oh, let's count. 1, 2, 3, and well, that's gonna be my aldehyde. All right, so 1, 2, 3. That's my propanol. So in this question, how do we approach it? We want to synthesize propanol from 3-hexane. The question is, how do we build this synthetic road? So first thing first, we think about the carbon skeleton. What we want only has 3 carbon atoms, and what we end up getting is, what we want is 3 carbon atom. What we start from is my 1, 2, 3, 4, 5, 6 carbon atom. So first step, we know that we have to somehow manipulate the carbon skeleton. So in this case, from an alkyne, directly breaking that alkyne bond is not straightforward because we don't have a reaction to directly break that alkyne bond. What we have is we have ozonosis to break an alkene bond. All right, so first step, the skeleton manipulation will be like, okay, so I want to do my skeleton manipulation of ozonosis. And that's gonna be an intermediate, like an alkene intermediate. So this is hydrogen, alkene. And let's say we have 1, 2, 3, 4, 5, 6, and we get to our 6 carbon skeleton. All right, and then I want to beautify it a little bit to say like, okay, this is actually equals to my 3, 4, 1, 2, 3, 4, 5, 6, 7. And I write 1, 2, 3, 4, 5, 6. And note the stereochemistry in this reaction is, well, it doesn't really matter because eventually we're breaking this carbon-carbon double bond. So stereochemistry is less important in this case. All right, yes.
I might be wrong, but when you say from hexane, does that mean hexane going to propanol? Because I feel like we're doing it the other way around.
We're trying to synthesize we're trying to synthesize propanol from 6-hexane.
Yeah, that's why I was wondering why we're starting with
doesn't matter. So it doesn't matter where you start in retrosynthesis problem. The reason retrosynthesis problem is complicated is you don't have a set way of which direction I'm going to start. If it works better to elongate my carbon-carbon chain from my reactant, that's my example one. Or if I want to say, okay, so ozonosis is the obvious way to quickly convert my carbon-carbon bond into carbon-oxygen bond and also alternating the carbon skeleton, then I start from the product. All right, so for retrosynthesis, there's no set way of like, hey, you always start from the reactant or you always start from the product. It doesn't work this way. It's more like whichever works for you, you start that way.
Okay, because I was wondering like if you could do the Na reaction to make that a double bond, and then you could do a toss polymerization to get that.
Well, okay, so if your mind is like clear enough of without doing like the carbon skeleton analysis, you just know you want to reduce it into double bond and cleave it through ozonosis, that's also fine, perfectly fine. There's no right way of doing it. I'm just showing like, from the very fundamental way of thinking, like right now, the best strategy for us in 30A to approach a retrosynthesis problem is to think about at which point we can alternate our carbon-carbon skeleton. Because it's easy. We only have two tools we can use at the moment to modify the carbon-carbon skeleton. And in here, what's the next step? Now then from here, going back to my hexane, what are we talking about? We're talking about using a reduction reaction to form your alkene from an alkyne. Now, whichever reaction you want to use, whether you use a Linder's catalyst, dissolving metal, that both of them should work. If you want to use hydroboration protolysis, that also works. Because we don't care about the stereochemistry in this process. We only want to reduce my alkyne into a alkene in this case. All right. So what is the overall reaction for this process after the analysis? We can write it out. What do we have? So we start by writing my alkyne. So 1, 2, 3, 4, 5, 6. You react it with Linder's catalyst. Or dissolving metal, both of them works, to get your intermediate, which is 1, 2, 3, 4, 5, 6. Now in this case, although both reaction works, you still want to be able to show the stereochemistry whenever you're drawing it. So in this case, I'm using the Linder's catalyst, so I'm keeping this bond as a cis bond. But if I'm using a different condition like Na and NH3 liquid, then I want to draw it in this way, in the trans fashion. Yeah.
Will we lose points if we don't do that? Or like is that?
You'll lose a small amount of points, like maybe 1 out of 10 or something. And from here, once we form the alkene, now both of them can undergo ozonosis. And what is the condition of ozonosis? That's step 1. You have O3 in an organic solvent. Step 2, you have dimethyl sulfide. And we're cleaving this center bond to form my aldehyde product. All right, so for this kind of retrosynthesis problem, unless we specify to show the mechanism, you do not have to show the arrow pushing mechanism for these retrosynthesis problem, unless we specify. Like there might be a scenario that we say like, hey, show the detailed arrow pushing mechanism of your first step or something like that. All right, so we'll review whatever we covered between midterm 1 to midterm 2 in our Wednesday's lecture. I'll probably spend more time reviewing like materials that just after midterm 1 because it's been a while. I will spend less time on retrosynthesis, but it doesn't mean this is not important. All right, this is equally important, and we'll come back with more discussion after the midterm exam. All right, see ya.